Thank you for the opportunity to speak at this special session of the Meteoritical Society, honoring the many contributions of Ed Scott to our science. I'm an astronomer who was introduced to chondrules about 6 years ago by my good friend and Wesleyan colleague, Jim Greenwood. I only knew Ed Scott through casual interactions at meetings, but was impressed with his knowledge, personability, and creativeness. He was obviously a model scientist. Answering the most basic questions about meteorites, what are they, what role, if any, do they play in planet formation, requires an understanding of what chondrules are and how they formed. One of the first papers I read on chondrule formation was a description of the splash model by Sanders and Scott. As an astronomer, I thought they had solved the problem, since the paper clearly describes how sufficiently hot material could be present in the asteroid belt at just the right time for chondrule formation. Recent work has only strengthened the evidence that chondrules formed within a very narrow time frame between 1.5 and 4 million years after CAIs. I am convinced that Sanders and Scott have it right. Chondrule formation had to wait for the decay of aluminum-26 to heat enough material in the interiors of large planetesimals, and ended when that energy source ran out. Additional support for this view comes from a recent simulation of asteroid growth by Weidenschilling, who found that 100-kilometer scale planetesimals form rapidly for a variety of plausible initial conditions. The size distribution of planetesimals quickly becomes bimodal, with most of the mass in large differentiated planetesimals, LDPs, that are the parent bodies of the iron meteorites. By 2 million years, there is only a small amount of primitive material remaining, mostly packaged in kilometer-scale SPPs, small primitive planetesimals. Our proposal, which we call the flyby model, differs from the splash model in that instead of using the mass of the hot material in LDPs directly to form chondrules, we use its energy in the form of near-infrared radiation to heat SPPs as they accrete to an LDP. The flyby model assumes that hot lava will occasionally break the surface of the LDP, either by collisions, as in the splash model, or by volcanic activity. SPPs orbiting the LDP in an accretion disk will be exposed to near-infrared radiation from the lava, providing the heat necessary for chondrule formation. This model is consistent with every observational constraint of which we are aware. Clearly, it accounts for the chondrule age distribution, just like the splash model. Thermal histories can be calculated from radiative transfer theory, and we can reproduce observed chondrule textures in laboratory simulations based on them. Size sorting may be a signature outcome of radiative heating, as Eisenhower and Busick have proposed. A unique aspect of our model is that it situates chondrule formation within a pre-existing porous solid, whose structure can partially confine the gas released by volatiles as they evaporate. We can account, therefore, for the high oxygen fugacity and sodium vapor pressure in which chondrules are known to have formed, and for the vapor trapping required by complementarity. We also expect the heated planetesimal to experience lithification during the encounter, just as in our chondrule experiments, which start with a fine powder and end with a well-lithified solid. The mechanism for this is hot isostatic pressing, or hipping, and it is a plausible means of lithifying whole chondrites while the chondrules are still warm, accounting for compound chondrules, cluster chondrites, and complementarity. The LDP is expected to produce a dynamo, which could be the source of the magnetic fields recorded by chondrules. Ultimately, the chondrite will accrete to the LDP, where it may suffer metamorphism from the still warm but not molten surface. It is extremely helpful, if not essential, to the flyby model that some of the accretion take place indirectly, that is, through a disk, so that an SPP or its fragments orbit the LDP millions of times before accreting, greatly increasing their chances of irradiation. Is an accretion disk plausible? We believe so. Stritauer and Tremaine have shown that an SPP that comes within 2.44 radii of an LDP will most likely be tidally disrupted. If the object was initially on a parabolic orbit, then half of the mass in fragments will remain bound to the LDP and accrete slowly over time. SPPs with larger impact parameters can also be captured whole through tidal dissipation of orbital energy and later disrupted and accreted. Also, glancing collisions can drain orbital energy from an impactor and lead to an accretion disk in a so-called hit-and-run collision. The importance of indirect accretion depends strongly on the velocity distribution of the accretors. For slow encounters, more than 50% of the accretion is indirect. At higher encounter speeds, most of the tidal fragments end up unbound, with the hit-and-run mechanism providing a floor of 1 or 2%. Is that enough? It depends on whether chondrules are a major or minor component of primitive asteroidal material. The chondrule flux at the Earth's surface is about 10,000 times less than the flux of all impacting material at the top of the Earth's atmosphere. Chondrules could, therefore, be as little as 1/100th% of the primitive material preserved in asteroids, although some of the total flux at the top of the atmosphere must be cometary. Fortunately, we are now beginning to get direct information on the abundance of chondrules on asteroids, and so far it supports our 2016 prediction that they will be rare. Here's the argument. It has been known for decades that small asteroids have bulk densities that are considerably lower than the meteorites to which they are spectrally analogous. Here we show 3 examples. The standard explanation has been that these are inefficiently packed rubble piles with macro porosities of around 40%. The alternative is that they are granular aggregates composed of low-density boulders, which often requires a boulder density below that of any known meteorite. 2 groups have recently employed linear mixture packing theory to estimate the macroporosity of Ryugu and thereby infer the density of its boulders. Using the surface boulder counts of Michikami et al. And assuming Ryugu is homogeneous, both groups found that its macroporosity is about 15%, with an error of just a few percent. Grott et al. Used a discrete form of the theory, and we used a continuous form. Based on these analyses, we predicted that typical Ryugu boulders must have a density lower than that of any meteorite, and that the Ryugu sample would consist of low-density particles with few, if any, chondrules. I am pleased to report that both predictions have now been confirmed. Our prediction for the density of Ryugu particles based on a macroporosity of 14% was 1.38 plus or minus 0.07 grams per cubic centimeter, less even than the density of the Tagish Lake meteorite. Here is the actual distribution of densities of Ryugu particles as reported by the Hayabusa 2 team in December. Our prediction is quite accurate and supports the hypothesis that the asteroid is reasonably homogeneous and not composed of known meteorites. The team also reported that no chondrules were found, again, consistent with our prediction. This is, of course, just one asteroid, and you cannot do statistics on a sample of 1. But we think there is good reason to believe that Ryugu is not an unusual asteroid, and that chondrules will be rare on most or all asteroids. Here's the argument. As shown here, the boulder size distribution of Ryugu is well fit by a log normal function. The reduced chi-square is only 1.13. This is a common distribution in geology, and there's no reason to suspect that Ryugu is exceptional. Linear mixture theory predicts that the macroporosity of any granular aggregate depends primarily on the size dispersion of the particles. This slide illustrates the prediction for a log normal distribution, but it is a general result of the theory that as the range of particle sizes increases, the macroporosity of the pile decreases. Larger than average particles replace space with rock, while smaller than average particles tend to fill in holes. No homogeneous pile with a particle size distribution similar to Ryugu's, for example, Bennu, could have a porosity much different than 15%. A macroporosity near 40% would be predicted only for a pile with a very narrow range of particle sizes or a stratified structure. Based on this, we predict that the density of particles in the Bennu sample will be similar to Ryugu, and that chondrules will be rare or absent in that sample as well. Summarize, the distinctive age distribution of chondrules strongly implies that aluminum-26 heating of large asteroids is a key factor in their formation, as Sanders and Scott discussed in proposing the splash model. The flyby model, which assumes radiative heating of pre-existing small porous planetesimals as they accrete to a large melted asteroid, can account for a wide range of observational constraints, including challenging ones such as complementarity, if at least some accretion is through a disk. Chondrules and chondrites are a dense, well-lithified form of primitive material that is arguably much rarer in the solar system at large than on the Earth due to atmospheric filtering. Chondrule formation models such as the splash and flyby should not be dismissed on the basis that they produce too few chondrules. Chondrules and chondrites may be a byproduct of extremely rare lithification events. Thank you.